Remainders are flawed for the uniform gauge, yet they're on Euclid built our common stage. Our prime roots shape what we become, irreducible truths that time can't overcome. We embrace classes not congruent to our trace. We dwell with our inverse face to face. When power surge and all seems gone, Fermat points us back to one.
Previously, we introduced the problem of computing modular exponentiation. Given a positive natural number n and an integer a coprime to n, we are interested in finding an exponent k such that a to the power of k is congruent to 1 modulo n. In this section, we focus on cases where the modulus is a prime number and introduce Fermat's little theorem. The theorem states that for any prime number p and any integer a that is coprime to p, a to the power of p minus 1 is congruent to 1 modulo p. For example, let p equal 5 and a equal 3. Since 3 and 5 are coprime, Fermat's little theorem applies and indicates that 3 to the power of 4 is congruent to 1 modulo 5. We have thus recovered the result previously achieved by brute force from the last section. To prove this theorem, let the set A be the set consisting of all multiples of the number a, where the multipliers range from 1 to p minus 1. In other words, a consists of elements of the form a, 2a, 3a, until p minus 1a. Also, let up be the set consisting of the integers from 1 to p minus 1. We now define a function f from a to up as follows. Let k times a be an element in a, where k is an integer between 1 and p minus 1. Due to the division with remainder, there exists a unique integer rk, which is between 0 and p minus 1, and is congruent to ka modulo p. Since p is prime, k must be coprime to p. Recall that a is also coprime to p. We conclude that ka is coprime to p as well. It follows that ka modulo p is not congruent to 0. Thus, rk cannot be 0 and must sit in up. We define the function f from a to up, which sends the element ka in a to this unique remainder rk in up for each k. In particular, this function f satisfies that for any element ka in a, fka is congruent to ka modulo p. We claim that f is a bijection. Concerning the injectivity, assume that k1 and k2 are two natural numbers between 1 and p minus 1, such that fk1a equals fk2a. That is, k1a is congruent to k2a modulo p. Now, since a is coprime to p, A inverse exists. Multiplying A inverse on both hand sides implies that k1 and k2 are congruent modulo p. Since each two different elements in up are distinct modulo p, we must have k1 equals k2, and the injectivity is proved. Once we have the injectivity, we see that the p minus 1 distinct elements in A are sent to p minus 1 distinct elements in up. Since up has precisely p minus 1 elements, this shows that f is also surjective. We have thus proved the bijectivity of f. Now, to finish our proof, note that by the bijectivity, the product of all elements in A, upon modulo p, is congruent to the product of all elements in up. The left-hand side is A times 2a times 3a until p minus 1a, which can be rearranged into p minus 1 factorial, multiplying a to the power of p minus 1. On the other hand, the right-hand side becomes p minus 1 factorial. Since p is prime, by Wilson's theorem, p minus 1 factorial is congruent to negative 1 mod p. Thus it implies in turn the Fermat little theorem after multiplying negative 1 on both hand sides. Now, if any step in the above reasoning sounds too abstract, let us go back to the example p equals 5 and a equals 3. Then the set A consists of 1 times 3, 2 times 3, 3 times 3, 4 times 3, which is the set of 3, 6, 9, 12, and U5 consists of 1, 2, 3, and 4. Now, after taking congruence modulo 5, f maps 3 to itself, 6 to 1, 9 to 4, and 12 to 2, which is clearly a bijection from A to U5. Multiplying all elements of A leads to 4 factorial times 3 to the power of 4, which is congruent to 3 times 1 times 4 times 2, and thus to 4 factorial after rearrangement. Now by Wilson's theorem, 4 factorial is congruent to -1 modulo 5, and the result follows. We have now completed the proof of Fermat's little theorem. Note that the assumption that p is prime cannot be dropped. For example, let p equal 6 and a equal 5. Since 6 is not prime, although 5 is coprime to 6, direct computation shows that a to the power of p minus 1 equals 5 to the power of 6 minus 1 equals 5 to the power of 5. Since 5 squared is 25, which is congruent to 1 modulo 6, 5 to the 5th power is congruent to 5 modulo 6. Thus, the statement of the theorem may fail when the modulus is composite. We have now completed the proof of Fermat's little theorem. Before concluding this section, let us make an important remark. In fact, in the last step of the proof, to cancel the common term, p minus 1 factorial on both hand sides, it is not necessary to know this term is congruent to -1. Rather, the existence of a multiplicative inverse for this term is sufficient. This observation leaves the door open for similar consequences for general positive natural numbers that are not necessarily prime. We will study this generalization in detail in the following sections.
신라 텐세